Assalamualaikum and good morning. First of all, I would like to say thank you to the Malaysian Society for Automatic Control Engineers, MACE, for inviting me to this periodical talk. I really hope that this presentation will give such an insightful knowledge for MACE researchers and opportunity for future collaboration and network. Welcome to my online presentation, and the title of my presentation today is Unlock Your World with Your Heartbeat. Evolution and Future Technology of ECG Biometrics. A little bit about myself. I'm Dr. Dzati Athiar Ramli from Intelligent Biometric Group's IBG, School of Electrical and Electronic Engineering USM. About my research interests, I've been involved in biometric research since 2007, and I've worked for several biometric modalities such as speech or voice, thumbprint, finger vein, and the latest one is ECG or electrocardiogram signal. At the same time, I've also employed several machine learning algorithms and artificial intelligence approach to my developed biometric system. Last but not least, blind source separation method in separating a mixed sound signal is also one of my current research interests. Before we proceed to the content of my presentation, here is the outline of my talk today. I will divide it into 3 sections. The first section will cover what is biometrics and the importance of biometrics, the drawbacks of implementing biometrics, and also the next generation of biometric types. Then we move to the next section, which is our main topic, ECG biometrics. I will include the evolution of ECG biometrics and ECG fundamental, followed by the current research and future possibilities, starting from the data acquisition, segmentation, feature extraction, and classification. Finally, the implementation of wearable ECG biometric device for biometric authentication will be presented. This includes the design of the wearable ECG detection kit for ECG data collection, followed by the development of ECG system. I am sure all of us are familiar with biometrics, and most of us have been using this technology as daily routine. For example, we use our fingerprints for system login. Many human characteristics has been researched so far by scientists for the purpose of human recognition. Those characteristics includes face, fingerprints, voice, and iris. Face and fingerprints are currently the most exploited biometric, which give a promising and reliable recognition. Commercial biometric products based on face and fingerprints are widespread, from smartphone to border control. The question now, why biometric is important? As we know, there are many social facilities that rely on authentication and identification systems such as airport, buildings, banks, websites, and smartphones. Authentication and identification are important to protect our identity, information, and possession. However, several of these facilities still depend on the traditional method such as key, smart cards, and passwords. These methods are vulnerable and less secure because key and smart card can be lost and stolen, and people might forget their password. Therefore, in the past decade, research on biometrics are rapidly increasing as biometric offers a perfect opportunity to solve the problems of the traditional authentication methods. There are many types of biometrics, and actually it can be categorized into physiological and behavioral biometrics. Examples of physiological biometrics are fingerprint, finger vein, face, hand shape, iris, ear, and DNA. Whereas for behavioral biometrics are voice, signature, gait, and keystroke dynamic. Of course, there are some requirements need to be fulfilled for any biometric trait to be accepted to be used for standard biometric system worldwide. First, the biometric trait that we want to choose must be universal, meaning that every person must have those traits. For example, everybody has their own finger, face, and iris. Second, the traits are unique for everyone so that it can be used to differentiate people. For example, everyone's fingerprint is unique. The third one is constancy, where it does not change significantly in the course of time. Others, of course, they must be good in performance and must be practical to be implemented. When we talk about biometric research, there are two terms that we often use. The first one is identification and the second is authentication. Identification system means the system will output the identity of individual who are the user of the system. While for authentication, or in other words we use verification, the system will accept or reject the claimant. ATM machine is the example where we must authenticate ourselves before we can draw our money. In spite of all the benefits offered by biometrics when compared with the traditional authentication system, there are several issues that remain to be solved. First is significant variability. This is referred as intra-subject or intra-class variability, since no two readings of the same biometrics modality are identical. Anatomical, physiological, or even environmental factors will affect the appearance of biometrics modality. For example, face may be presented under various expressions, different lighting settings, or with occlusion, for example, glasses and hats. So the challenge is to design algorithms that are robust by addressing appropriate feature extraction and classification. The other issues are related to circumvention, privacy, and data security. In general, we can say that we have three generations of biometric research. In the beginning, most of the research focused on external biometrics like fingerprint, face, and iris. After that, the trend moved to the internal features like fingerprint, which is claimed to be more robust as the internal features are harder to imitate compared to voice, face, and fingerprint. As voice can be recorded, so they can use the recorded voice for authentication. Similar to face, it can be captured easily, and fingerprint, it can be falsified using gummy product. At that time, the research also focused towards contactless biometrics so as to tackle the issue of hygiene. Nowadays, the current research trends are now on the use of wearable and mobile biometrics, and at the same time, of course, with the integration of IoT technology and cloud computing. In terms of biometric traits, research toward the medical biometrics like ECG and EEG, which can be used for diagnostic purpose, are currently researched. Okay, now let's proceed to the second section, which is our main topic, ECG biometrics. Recently, a new set of biometric traits called medical biometrics like ECG has gained momentum. And why? First, ECG signal present in all living individuals. The possibility of utilizing them for continuous authentication, since they can provide a fresh biometric reading for every couple of seconds. Then, ECG signals are difficult to counterfeit, or at least at the sensor level. So, robustness to circumvention, replay, and obfuscation attack can be guaranteed. Third, ECG is one-dimensional psychological signals, which ensures low computational effort. And last but not least, the ECG signal provide additional information related to psychological and physiological state and clinical status, which maybe becomes an interest for other applications. As it has been stated in the first section, there are several requirements needs to be fulfilled for ECG to be endorsed as biometric traits. First is universality, that is the ability of collecting the biometric samples from the general population. Since the ECG is a vital signal, this property is satisfied naturally. Second is permanent, in other words, is stability over time. This means that the ECG signal must be capable to perform the biometric match against templates that has been designed earlier in time. For these arguments, even though the specific local characteristic of ECG pulse may be changed due to the physical and physiological activity, the overall critical wave and morphologies are still observable. Third is uniqueness, which guaranteed by its physiological origin as shown in this figure. As we can observe, there is a large inter-subject variability due to the various parameters that control the generation of the ECG waveform. Fourth is robustness to attack. The appearance of the ECG waveform is the outcome of electrical activity of the heart over time. Controlling the waveform or attempt to mimic ECG signal is extremely hard. To the best of our knowledge, there is currently no means of falsifying an ECG waveform and presenting it to a biometric recognition system. Fifth, ECG offers natural liveness detection. The recognizer can trivially ensure sensor liveness, compared to iris or fingerprint, which require additional process to read the result. Lastly is continuous authentication. When deployed for security in monitoring environments, a fresh reading can be obtained every couple of seconds to re-authenticate an identity. Next, we proceed to the anatomy of ECG. Here, I will explain how ECG signal is produced by our heart, and from that understanding, we can relate why ECG can be used as biometrics due to its inter-subject variability. We can say that our heart is a pump. A contraction of myocardial muscle cell contract in response to electrical currents that cause the depolarization of those tissues by triggering action potentials. The flows of depolarization and repolarization are electrical currents generated through the heart. Heart size, muscle thickness, and shape of the heart dictate the path of the current signals, which make it unique for every person. These electrical currents can be detected and measured through electrode placed on the body in a process called electrocardiography. The resulting signal is called a cyclic repetition deflection, as stated as PQRS and T wave in this figure. Next, we describe the different stages of ECG data acquisition evolution from recent development to future settings and their potential for ECG biometrics. The first is medical configuration setting with the standard 12-lead configuration that allows the acquisition of an ECG signal in 12 channels. In early ECG biometric research, this setting were commonly used. However, several limitations such as large number of electrodes, uncomfortable placement, and limited movement are the setback. For off-the-person setting, the wet electrode was replaced by dry metallic electrode, and the number was reduced to 2 or 3, and the placement was confined to upper limbs. Recently, a few initiatives by developing wearable technologies for ECG acquisition. This paved the way for better future technologies that can acquire ECG signal at short distance without requiring contact. For wearable, the future product should continuously monitor the user ECG while only touching their wrist or inside the pocket separated from body. Now we move to the current research on ECG feature extraction. Several feature extraction methods have been proposed for ECG biometrics, and they can be categorized into 3 groups: fiducial method, hybrid method, and non-fiducial methods. Fiducial method extract temporal, amplitude, area, angle, or dynamic features from the characteristic point on the ECG signal to create feature vectors that are used as input to the recognizer. Hybrid use the RPIC to achieve heartbeat waveform segmentation, assuming either the full waveform or a subset of it as input to the recognizer. Non-fiducial method extract information from the structure of the signals without the need of any reference points, but rather segment the entire ECG trace into non-overlapping or overlapping windows and extract features from those windows. Features like wavelet coefficients and autocorrelation coefficients are utilized. However, the ideal feature extraction would be the one that combines the condition for high performance offered by fiducial approach with the robustness to noise and variability that offered by the non-fiducial approach. Next is about the ECG classifiers. Classifiers that are commonly used for the ECG biometrics are generally either support vector machine, nearest neighbor classifiers, or artificial neural network. As deep learning are quickly revolutionizing several areas in pattern recognition, several research using recurrent neural network (RNN), convolutional neural network (CNN), and long short-term memory are recently reported. Let's now proceed to the next section, implementation of wearable ECG biometric device for biometric authentications. This includes the design of the wearable ECG detection kit for ECG data collection, then followed by the development of the system. First, we proceed to the methodology. The proposed ECG biometric system can be summarized as in this figure, which consists of 4 main modules: the wearable heartbeat detection kit, Android platform application, offline and online database server, software module for segmentation, feature extraction, and classification processing, and the hardware interface which can function for automatic security door. In order to design a portable and wearable heartbeat detection kit, flexibility of the device is the main concern. This device is designed as a wearable bracelet to be used by user for system login. 3 electrodes are used to detect the ECG signals instead of 12 electrodes, which are normally used in standard clinical 12-lead ECG devices. The placement position of the electrode is shown here. By placing a finger on the top side electrode while the user wrist is in contact with another 2 electrodes, an electrical circuit is now complete. Thus, ECG signals are able to be detected by the device. Since the ECG signal voltage is normally just a few millivolts or less, thus it needs to pass through amplifier stage in order to amplify and pre-process the signal before it can be executed to the back-end system. The block diagram of heartbeat detection kit is shown here. In general, the heartbeat detection kit is formed by 6 main parts: instrument amplifier, high-pass filter, north filter, low-pass filter, analog to digital converter, and signal transmitter. In general, the software written consists of segmentation, feature extraction, and pattern matching algorithms. It must be written module to modules according to the flow illustrated in this figure. The coding should be able to segment the signal into arrays of independent paths. Subsequently, signal preprocessing coding is written for signal denoising. Dealing with signal and session variability is a common problem in biometric recognition system, since biometric signal is frequently inconsistent over time. Health, aging, emotional conditions, and different recording settings are some of the factors that contribute to the variability issue. This causes the 2 samples of the same subject tends to be different from each other, hence giving a mismatch effect between the enrollments and testing conditions. With the rise of portable and wearable acquisition setting, signal variability is becoming the main problems that need to be solved in order to achieve a good performance system. Preprocessing and feature extraction will need to be improved, and reformulated for acceptable reliability. Currently, in this project, we are implementing I-vector algorithm for the feature extraction and classification. There are many methods that can be used for denoising. In the second figure, here the wavelet denoise process is used to obtain the denoised ECG. It can be shown that the peak of the QRS complex can now be observed clearly. The wavelet denoising can be divided into 3 steps: decomposition, adjustment of wavelet coefficient, and signal reconstruction. For example, 10th order Drawbacks wavelet is used to decompose the signal to represent the detail component of the signal. Since lower scale detail contain higher frequency component of the signal, therefore by lowering the coefficient of the lower scale detail can reduce the high frequency noise. Consequently, the thresholding process is employed by replacing the coefficient values that are less than the threshold values with zeros. After thresholding, the signal is reconstructed. In this study, hybrid method is used for segmentation. Since our peak is the highest amplitude, therefore it is obvious to be captured and used as separation point for the segmentation. It is important to pick only the features that are unique, significant, and least corrupted by noise. For this purpose, several feature extraction methods, which can be categorized as fiducial, hybrid, and non-fiducial approach, can be used. In this figure, the example of the wavelet transformation is used to decompose the ECG pulse into their corresponding wavelet coefficients in order to extract the features. Currently, with the start of deep learning methodologies, all these conventional techniques can be replaced with deep learning approach. However, computational cost is another limitation that needs to be addressed as well. The unique properties of ECG signals among people can be observed after the feature extraction stage. This observation also proves that why ECG signal can be used as biometrics. For example, the value of 9 coefficient of individual A is only about 50 to 100, while individual B is about 300 to 350. At another point, individual A has about 350 to 400 on 17 coefficient, while individual B has only about 250 to 300. Here I would like to share the method that we use in order to solve the variability issues. Over the years, solving the variability problems by subspace representation concept has become prevalent. Hence, it motivates us to validate a recognition algorithm based on factor analysis perspective. The overall flow of our method is shown in this figure. After the pre-processing stage, the segmented signal is first extracted using Mel frequency capstrom coefficient MFCC. Then we model each supervectors extracted from the Gaussian mixture model GMM into 2 different vectors, which are subject and session independent supervectors based on joint factor analysis GFA algorithms. However, for the second model, which is based on I-vector approach, the supervectors extracted from the Gaussian mixture model is modeled to be a single total factor only. In joint factor analysis GFA, a signal is represented by a supervector M that consists of additive components from subject subspace and channel subspace. The supervector M is defined as this equation, where M is a subject and channel independent supervector, generally from Universal Background Model UBM. V and D define a subject subspace, eigenvoice matrix, and diagonal residual respectively, and U define a session subspace, eigenchannel matrix. The vector y, z, and x are the subject and session-dependent factors in their respective subspace, and each is assumed to be a random variable with a normal distributions. In I vector, S is the supervector that can be represented as this equation. Here, M is the subject and channel independent background UVM supervector. T is the total variability subspace, which is a rectangular metric of low rank, while W is the random factor having a standard normal distributions. The components of W is also referred as total factors, represented as a new vector, namely identity vector or I vector in short. The extraction of I vector is based on the bound-wave zero order and centralized first-order statistics. For extraction of supervectors, UBM-GMM is selected with the goal of extracting subject-independent information while projecting capsular features from previous steps. This information will then be passed to I vector for extracting a fixed-length, low-dimensional data representation. This study evaluates the effects of different Gaussian components from 8 to 128 in a doubling sequence for I vector with compensation techniques. As the I vectors modelings contain speaker and channel variability information simultaneously in one space, carrying out channel compensation technique in the total factor space is required in order to remove the nuisance effect. The channel compensation approach plays a major role in the I vector speaker recognition system. For channel compensation to be possible, the channel variability has to be modeled explicitly. Three compensation methods for the I vector are usually employed, which are whitening, linear discriminant analysis (LDA), and within-class covariant normalization (WCCN). Now I would like to share our findings regarding the I vector performance in authenticating person based on ECG signal. The result is promising. Here the system performance is evaluated using equal error rate EER on the development set and the half total error rate HTER on the evaluation set for GMM, GFA, I vector PLDA, I vector LDA, and I vector WCCN. From the experimental result, we observed that the I vector PLDA achieved the best performance in most experiments. The best ER performance, 2.156%, was given by the I vector PLDA system with 16 GMM component, and for the HTER performance, the best result was also from the I vector PLDA system with 0.746% with 16 GMM component. Finally, that brings us to the end of my presentations. I would like to summarize by saying that ECG has a big potential to be one of the future biometrics, and this is possible by focusing on the problems and challenges that need to be addressed, especially regarding the practical data acquisitions, enhancing the software of the feature extraction and classification algorithms by using the deep learning approach, for example, and towards the implementation of IoT. I really appreciate that I have had this opportunity to present this topic to you, and thank you very much for your time and attention. If anyone would like more information or has any question, please feel free to contact me at dzati@usm.my. Thank you very much and see you next time.